In section 8.6, we're going to look at the trigonometric form of a complex number. This form will have a lot of advantages, especially as it pertains to the multiplication, division, and taking exponents of complex numbers. So we've already studied the standard form of a complex number. Let's call it the form a plus bi. We can plot it in the complex plane. We would go a units along the real axis, b units along the y-axis, and that would give us our point. In order to define the trigonometric form of a complex number, let's think of the point z equals a plus bi as being a distance r from the origin at an angle theta, which would be an angle of rotation from the positive real axis. If that's the case, then A, B, and R are all sides of a right triangle with acute angle theta, and we can set up some of the same trigonometric relationships we've done in the past. In particular, we would know that the cosine of theta would be equal to A over R, which means that A would be equal to R cosine theta, and the sine of theta would be equal to opposite over hypotenuse. That would be B over R. Therefore, B would be equal to R sine theta. So using these expressions in place of A and B in the standard form would result in what's referred to as the trigonometric form of a complex number. We can write it as R times cosine theta plus I sine theta. The expression z equals r times cosine theta plus I sine theta is called the trigonometric form of the complex number. The r value, which is the distance of the complex number from the origin, that value r is called the modulus, and the angle theta used in this expression is called the argument of the complex number z. We want to make sure that every time we write the argument, we would prefer for it to be in standard form, so we want theta to be between 0 and 2 pi. When we sometimes have to work backwards, if we want to find the angle theta, we can use the following. If theta is in quadrant 1, or z lies in quadrant 1, then theta can simply be found by using the tangent inverse of b over a. If z lies in quadrants 2 or 3, then you can find theta by doing pi plus the tangent inverse of b over a. And if z happens to lie in quadrant 4, then theta can be found by doing 2 pi plus the tangent inverse of b over a. For example, in part 1, they want us to write the complex number z equals to negative 2 minus 2 square root of 3i in trigonometric form. In order to do this, we're hoping to come up with an expression of the form z equals r times cosine theta plus I sine theta. So it's up to us to find the value for r and the value for theta. Let's find r first. R was defined as the square root of a squared plus b squared. For this complex number, a is negative 2 and b is negative 2 square root of 3. So we're going to have the square root of negative 2 squared plus negative 2 square root of 3 squared. R is equal to, this is going to be the square root of 4 plus, when we square a product, we square both terms. Negative 2 squared is 4, and then the square root of 3 squared would be 3. R is going to be 4 plus 12 under a square root. So this is the square root of 16, which is going to be equal to 4. So the modulus of this complex number is 4. We can go ahead and plug that in here. The only thing left to determine now is what is the value for the angle theta. Well, let's take inventory. What quadrant would this angle be in? This is going to be what quadrant would this z complex number be in? Well, negative 2 and then negative 2 radical 3 is going to be somewhere in quadrant 3. So this angle is going to be in quadrant 3. If z is in quadrant 3, then we're going to use pi plus tangent inverse of b over a. So theta is going to be equal to pi plus the tangent inverse of b over a. That's negative 2 square root of 3 divided by negative 2. Theta is equal to pi plus, this is going to be the tangent inverse of radical 3. If we think about where would the tangent have a value of radical 3 at, that angle, because tangent is sine over cosine, that should be pi over 6. Because the tangent of pi over 6 is equal to radical 3, the tangent inverse of radical 3 is going to be pi over 6. So this is going to be pi plus pi over 6 after common denominators. This will give us 7 pi over 6. So the argument of this complex number is 7 pi over 6, and that's the last thing we need in order to complete the trigonometric form. So our answer is 4 times the cosine of 7 pi over 6 plus I sine of 7 pi over 6. So that's our complex number now written in trigonometric form. Let's take a look at example 2. In example 2, we're presented with a complex number in trigonometric form, and we're asked to write it in standard form. So we want to write this as z equals a plus bi. So really all we need to do here is find the value of the cosine of negative pi over 3, the value of the sine of negative pi over 3, and then just go ahead and distribute the radical 8 in. In order to do that, we've done a lot of calculations like this before in the past. Typically, this angle is not in the standard range. So what you would do is find a coterminal angle that would be, find the quadrant, do reference angles and all that good stuff. But it becomes far more convenient just to simply use the even and odd identities because the angle is negative. For example, we know that because the cosine function is an even function, that the cosine of negative pi over 3 is going to be equal to the same thing as the cosine of positive pi over 3. And then because the sine is an odd function, the sine of negative pi over 3 is simply going to be the negative of the sine of positive pi over 3. And that's extremely convenient because now we know pi over 3, that's one of our angles from the first quadrant. So those values we should have memorized. The cosine of pi over 3 is a half, and the sine of pi over 3, that would be radical 3 over 2. So we get z equals, if we distribute it through, the square root of 8 over 2 minus I times the square root of 24 over 2. We can do a little bit better here because actually 8 and 24, they're both divisible by perfect squares. 8 is the square root of 4 times the square root of 2 over 2. 24 is the square root of 4 times the square root of 6 over 2. This should be equal to 2 square roots of 2 over 2 plus 2i square root of 6 over 2. And then after we do that simplification, we get some cancellation. These 2's cancel, those 2's cancel, and we would get for our final answer z equals the square root of 2 plus I square root of 6. This is the same complex number, but now it would be written in standard form. The next thing we're going to look at is multiplication and division of complex numbers in trigonometric form. Suppose we have two complex numbers, let's call them z1 and z2. Suppose z1 has modulus r1 and argument theta 1. z2 has argument theta 2 and modulus r2. If we want to multiply them and take their product, in trigonometric form, the product of two complex numbers is simply going to be the complex number whose modulus is the product of the moduli, that's r1 times r2, and whose argument is going to be just the sum of the arguments theta 1 plus theta 2. And this is really convenient because it turns what would otherwise be a distributive problem type question utilizing the fact that I squared equals to -1 into just a basic multiplication and addition problem of real numbers. Let's take a look at example 3. They say find the product of z1 and z2. So let's go ahead and do this. To do z1 times z2, we're simply going to multiply their moduli. This is going to be 3 times 2. And then it's going to be the cosine of, now we just have to add the angles. Pi over 4 plus 3 pi over 4 plus I times the sine of pi over 4 plus 3 pi over 4. This is equal to 6 times, this is going to be the cosine of pi plus I sine of pi. We could leave it like this if they didn't ask for anything else. This would be the answer in trigonometric form. Let's go ahead and write it in standard form because we get a very nice answer on this. We know that the cosine of pi is -1. The sine of pi is 0. So this works out to be simply 6 times -1 or -6. So the product of z1 and z2 would be equal to a real value, and it's the real value -6. Let's take a look at example 4. We have another multiplication of complex numbers in trigonometric form. The answer to this product is going to be the product of the moduli. That's going to be 2 times 8 times, we're going to have the cosine of the sum of the angles. That's going to be 2 pi over 3 plus 11 pi over 6 plus I sine 2 pi over 3 plus 11 pi over 6. This is going to be equal to 16 times the cosine. When we add those angles together, 2 pi over 3 plus 11 pi over 3, you would need to get common denominators. That would be 6. 2 pi over 3 is the same thing as 4 pi over 6 plus 11 pi over 6 is going to be equal to 15 pi over 6. And 15 pi over 6 would reduce, because it has a common factor of 3, to 5 pi over 2. So this would be 5 pi over 2 plus I sine of 5 pi over 2. This is the correct answer, but we couldn't leave it in this form. It looks like it's in trigonometric form, but the argument is not in the standard range. 5 pi over 2 is more than 2 pi. So we would want to find a coterminal angle to 5 pi over 2 by subtracting 2 pi. That's going to be 5 pi over 2 minus 4 pi over 2, which would give us pi over 2. So in proper trigonometric form, it's 16 times the cosine of pi over 2 plus I sine of pi over 2. If we want to write this in standard form, it's going to be 16 times the cosine of pi over 2 is 0. The sine of pi over 2 is 1. And so this would work out to be 16 I.